All right, let's jump right in. Have you ever just stopped and wondered how an AI actually figures things out? I mean, how does it solve a really tricky problem? Well, in this explainer, we're going to pull back the curtain on the core strategies AIs use to tackle what seems, well, pretty much unsolvable. So, let's get right to it. How does an AI solve a puzzle, like one of those sliding tile games? Or how does it find the absolute best route for a delivery van? Or even figure out the checkmate move in a chess game? You might think it's some kind of magic, but really it all comes down to pure logic and a solid strategy. And this right here, this is the big idea that unlocks everything. It's pulled right from your course material. Numerous AI challenges can be framed as search problems, and that's the key. Suddenly, problem solving isn't this abstract thing, it's a hunt. It's a search for the right answer hidden among maybe millions of possibilities.
Which leads us perfectly into our first section here, AI's universal puzzle, the art of the search. We're going to break down the absolute essentials, the building blocks an AI uses to understand any problem you throw at it.
Okay, so what does an AI need to even begin its search? It really just boils down to three basic things. Think of it like a recipe. First, you need a starting point, right? We call that the initial state. Second, you need to know what you're looking for, a way to tell when you've actually found the solution. That's the goal test. And finally, it needs a rule book. It has to know all the possible moves it can make from wherever it is. Your course material calls this the successors function, or just SUX for short.
All right, let's see how this actually plays out. We're going to start with the most fundamental kind of search. I want you to imagine you're dropped into a huge maze. You have no map, no compass, no hints whatsoever. That feeling? That's the perfect way to think about what we call uninformed search. So what exactly is uninformed search? Well, the definition says it all. It's when the AI, or agent, has zero extra information. It knows two things. Am I at the goal yet? And what are my possible next steps? But, and this is the important part, it has no idea if going left is better than going right. It's completely fumbling around in the dark. That's why another name for it is, you guessed it, blind search. This really breaks it down perfectly. On one hand, you've got what the agent knows, which is basically nothing. Have I won? And where can I go from here? That's it. On the other hand, look at what it doesn't know. It has no way to tell which move is more promising. It has no sense of direction, no feeling of getting warmer to the solution. It's just blind. So, if you're searching blind, how do you even begin to do it in an organized way? You can't just wander randomly. Well, it turns out there are two classic strategies that are total opposites. One searches wide, and the other searches deep. All right, first up is Bread's First Search, or BFS. The best way to think about this one is to imagine a very cautious, very methodical explorer. It refuses to go any deeper into the maze until it's checked every single doorway on the level it's currently on. The ripple effect is the perfect way to describe this. You can see it here. It starts at the center and explores that first ring of neighbors completely. Only when that entire layer is checked off does it move to the next ring further out. It just expands outward, one single layer at a time. So how does it keep everything so organized? The secret weapon is a queue. Like a line at the grocery store. It's a first in, first out system. You start with your first position. You check out all its neighbors and tell them to get in line, at the back. Then you just serve whoever is at the front of the line next. This simple rule guarantees you finish exploring level 1 before you even start on level 2. Okay, now let's do a complete 180. The other approach is Depth First Search, or DFS. And if BFS was our cautious explorer, DFS is like a determined cave diver. It picks one tunnel and just goes for it, diving as deep as it possibly can down that one single path before it even thinks about coming back to try another one. And you can see that exact behavior right here. It picks that one branch on the left and just keeps going, deeper, deeper, deeper. It only backtracks just one step when it hits a dead end and has no other choice. It's got total tunnel vision, and that's the whole point. So how does it work? Instead of a line, DFS uses a stack. Think of it like a stack of plates. It's last in, first out. When it finds new options, it stacks them right on top. And for its next move, it always grabs the one it just put on top. This forces it to always follow the newest, deepest path it's just found. So, okay. We've got two completely different strategies. One goes wide, one goes deep. Which one is the right one to use? Well, that's what this next section is all about. The algorithm playbook, choosing your tool.
So, which one's better? That's the million-dollar question, right? And the answer, which you'll hear a lot in computer science, is it depends. It completely depends on what your problem looks like and what you care about most.
This chart lays out the trade-offs perfectly. Let's just go down the list. Completeness, will it for sure find an answer? BFS, yes. DFS, nope. It can get stuck in a loop forever. What about optimality? Will it find the best answer? Again, BFS says yes, as long as each step is equal. DFS, no guarantees at all. Time? Well, they can both be pretty slow. But here's the kicker. Space. Memory. BFS can use an enormous amount of memory. But DFS? It's super efficient with memory. That's its big advantage.
So let's be real about DFS. Its big win is memory usage. For gigantic problems where BFS would just crash your computer, DFS might be your only hope. But you're making a big trade-off. It's not guaranteed to find a solution, and even if it does, the first one it finds is almost never the best one. You could get really lucky or really, really unlucky.
Now, obviously, people tried to get the best of both worlds. You've got other strategies like iterative deepening, which tries to get the memory savings of DFS but still guarantees it'll find a solution like BFS does. And then you get into what's called informed search with things like A*, which uses educated guesses to be smarter. But even A* isn't perfect. On really huge problems, it can also just run out of memory. There's always a trade-off.
All right, that was a lot of theory. Nodes, queues, complexity, all that stuff. So let's land the plane and talk about why any of this actually matters in our final section: puzzles, paths, and reality.
Because this stuff isn't just for classroom puzzles. These search algorithms are the engines running under the hood of so much modern tech. Think about robotics, planning the perfect motion for a robot arm, or logistics, finding the absolute fastest delivery route. Even in video games, this is how the AI opponent figures out its next move to beat you. It's all just searching for the best possible plan.
And if you need just one example to remember, think about this. Every time you use Google Maps or any GPS, you are watching a search algorithm do its magic in real time. It's solving a massive puzzle. Out of all the thousands of ways to get from here to there, find me the best one, the one that costs the least time. But that leaves us with one last big question, doesn't it? These blind searches are great at finding the path with the fewest steps, but what happens when the best path isn't the shortest one, you know? What if one route has terrible traffic or another has a bunch of tolls? To solve that kind of problem, you need to be a little bit smarter. You need what's called an informed search, and we'll get into that next time.